Hello, class. This is a walkthrough of There's Been a Crime, which we did in class on Friday. And I'm just going to go over some of the main ideas that I hope came across. So the important thing to realize from the prompt is that this vase is broken, but what broke the vase was something falling from the balcony. An object fell from the balcony, probably a planter, right? We learned that there are red geraniums, sorry, scattered about the crime scene, right? And they come from potted plants that are on the outdoor patio. So what that means is one of these potted plants fell from one of the upper levels and it hit the vase. But when that happened, a car was in front of it and it obscured the collision. So we didn't see the object actually hit. We didn't see that thing. We didn't see the planter actually hit the vase because it was obscured by this car. So what we're really trying to figure out is where this vase fell from, right? We want to, where the planter, we want to figure out where the planter with the red geraniums, where it fell from, right? This potted plant fell, right? And it hit, the potted plant fell and it hit this vase. And we want to figure out where that potted plant came from. Basically what floor it came from. So that's the main objective. So we're given this map, and from this map, you can actually measure with your ruler and see that this is 3 centimeters. So we know that 3 centimeters equals 6 meters, which basically gives us a scale of 1 centimeter equals 2 meters in reality. That's our scale. And we know that the car, this is the car, it was at the stoplight, and here was the scene of the crime. Now, the important thing to realize is which part of the car had to actually get in front of the vase. Was it the front of the car? It was not the front. The front of the car was right here, right? If the front of the car was here, it wouldn't obscure the collision. It has to be the middle of the car. And we see that verified later in another clue. So it's really this distance that we're looking for. And if you look at that distance, and you measure it, we see that that comes out to be 6 centimeters, which is 12 meters in real life. So the real distance that the car went was that 12 meters. So moving on to the next clue, we see these oil drops. And so this oil drop fell while it was, that's the 0-second mark. That's while it was at the stoplight. And this is 1 second after it started driving. And this is 2 seconds after it started driving. And what we want to do is figure out the acceleration of the car. So since we know the acceleration of the car, we can use that to maybe calculate other things. So we can use the second equation of motion, delta x equals v naught t plus 1/2 at squared. And if we start here at t equals 0, that would be when it was at rest. So at rest, v naught is 0. So that means delta x equals 1/2 at squared. And we want to solve for a. We want to calculate that acceleration. So we multiply both sides by 2 over t squared times 2 over t squared. And that gives us a equals 2 delta x over t squared. So we have to find the right delta x and the right t. So we could look at this interval, or we could look at this interval. We can't look at this interval, the interval from, so we can go 0 to 1 second or 0 to 2 seconds. We can't look at the 1 to 2 second mark for this, because then we would need to know this V naught value, right? We're saying that we're starting from rest. We could calculate it and then do it, but it would be a little extra work. It's a little burdensome. So let's look at the 0 to 1 second interval. In that case, we would have A equals 2 times delta x would be, this is 1 meter, so to here is 1.5 meters. So that would be 2 times 1.5 meters over, that would be 1 second squared. That's from 0 to 1. So that would be 3 meters per second squared, right? 2 times 1.5 is 3, and 1 squared is 1. So 3 divided by 1. We could also look at the whole interval from 0 to 2 seconds. That would be 2 times this distance from here all the way to here, which we see that's 0, that's 1 meter, 2 meter, 3 meter, 4 meter, 5 meters, 6 meters. And that would be a 2 second interval, 2 seconds squared, which is, that would be 12 meters over 4 seconds squared, which is 3 meters per second squared. And we see that these agree. Some people want to find V between 0 and 1 and V between 1 and 2, and then calculate the acceleration that way. You could do that. And this speed here between 0 and 1, that would be 1.5 meters per second. I'll do it in a darker blue. 1.5 meters per second. That's from 0 to 1, as it goes 1, and then V12 would be, this is 4.5 meters per second. So you could calculate the acceleration that way. A equals delta V over T, but it's really that a delta T. So that's 4.5 minus 1.5 meters per second. The thing is, right, at what time does it actually have this 1.5 meter a second time? That's actually at the moment halfway between 0 and 1 second. That's really at the 0.5 second mark. And when does it have this 4.5 second mark? Halfway in between 1 second and 2 seconds, which would be 1.5 seconds. So that turns out to be 4.5 minus 1.5 is 3 meters per second over 1.5 minus 0.5. That's 1 second. So 3 meters a second squared. And again, we see agreement. So the acceleration is 3 meters a second squared. However you calculate it, you've got to be able to calculate it the best way. Using equations of motion are probably the best way to do this, because you don't have to worry about the little intervals of your average velocities. Moving on to clue number 3. We learned that the lobby is 4.5 meters tall, and then each floor after that is 3 meters tall. But there's a railing, a balcony railing of 1 meter. So we want to develop an equation to calculate the railing height for any level. So the height at any level, you're going to be above the lobby is going to be, you're going to have to deal with that lobby height, 4.5 meters. Plus Well, however many floors you are, there's going to be 3 meters per floor. So that's going to be 3 meters times the number of floors. But the thing you have to realize is that when you're standing on, let's say you're standing on the 6th floor here, you're not at the top of the floor, right? You don't stand up, you're not at the roof of that floor. You're basically standing on the ceiling of the 5th floor. So if you're at the 6th floor, you're really standing on top of the 5th floor. So it's really n minus 1, right? You're really, that your height is n minus 1 floors. And then you are up 1 additional meter. That's because of the balcony railing. So this is the lobby. This is the number of feet you are, the number of meters, the height per floor. And then this is the railing height. So if we expand this, h equals 4.5 meters plus 3 meters times n minus 3 meters plus 1 meter. So h equals 3 meters times n plus 4.5 minus 3 plus 1, that is plus 2.5 meters. And that is a mathematical model, way to calculate the height at each floor. And that's one of the things we want to know, is what floor it fell from. Okay, so going on to clue number 4. Clue number 4 just tells us that these floors are all missing the planter. So the planter could have gone missing from one of these 3 floors. And there's some information we gather from each of these people, but that it's not really that important. What's really important here is that we're either on the 8th floor, the 12th floor, or the 16th floor. And from our previous models, we can figure out what those heights are. We can figure out the height of each of those floors from our clue number 3, the actual height above the ground. Moving on to clue number 5. We get some verification that where did the planter, where was the car when the planter hit the vase? Well, it was here. It was not in the front of the car. We don't see the debris over here. We see the debris on the door, right, on the middle of the door. So it's on the middle of the car. That's some verification that the car, the middle of the car was in front of the plant, which makes it that full 12-meter distance that the car had to drive. We also learned that our model using constant acceleration, that acceleration was constant, so we could use those constant acceleration formulas. All right. And we learned that there was some plan to drop something at the same time the car passed in front of it. That was part of the plan of the person that called the driver. Finally, we learned that there is a debris field on the concrete. We see that the debris had a diameter of 0.9 meters, right? The debris, this is all the shattered pieces of the planter that was dropped. So this will be important in the next clue. So moving on to clue 6, we did a test to determine what impact velocities make certain debris fields, okay? And it doesn't tell us, but it says to develop an equation to relate diameter to impact speed. So that's what we're trying to figure out. And it doesn't tell us, but I told you that you should use a linear model, like y equals mx plus b. And your variables, x and y, those are going to be the diameter of the field and the velocity of the impact. Now, when you go to the scene of the crime, what is the thing you're going to see? Are you going to see the speed of the vase when it hit the ground, the impact speed, or are you going to see the debris field? The debris field is the thing we actually measure. So the debris field should be our independent variable, D, and our dependent variable, sorry, so our independent variable should be the diameter. That's the thing we're measuring. And the thing we're going to calculate is that velocity of impact. And then that y-intercept would be an initial velocity. And we can use any of these two values to calculate that slope. So we want to calculate what that slope is. So let's go ahead and do that. I'm going to look at the last two values. So that would be 24 minus 22 meters per second. The difference in the velocities, right? The difference in these velocities, that's the vertical, the y, over the difference in the x, the horizontal values, which is the diameters. So that would be 0.7 minus 0.6 meters. And these meters then cancel, giving us units of 1 over seconds, and that's going to be 2 over 0.1, 1 over seconds. So that 2 over 0.1 is 20 inverse seconds. All right. Is this a good model? Is this a good slope? Well, we could compare it. We just did 24 and 22. Why don't we compare it to 20 and 18? Did we get the same thing? Right. So m equals 20 minus 18 meters per second over 0.7 minus 0.6 meters. And we get 2 over 0.1 inverse seconds. That is the same thing. So we see our slopes reasonably working out. And so the last thing to figure out is what this V naught is. So we now know that, right, we've got that V equals 20 inverse seconds times the diameter plus V naught. And we need to pick any point. So I'll use this one right here. You could use any point. So that would mean 20 meters per second equals 20 inverse seconds times a 0.5 meter debris field, right? This value is here and this value is here, plus V naught. So that leads us to 20 meters per second equals 20 times 0.5 is 10 meters per second plus V naught, which means moving that 10 over to the other side, that gives us V naught equals 10 meters per second. So that means that this value here is 10 meters a second. That is our mathematical model. And you could test it with any of these values and it should work out. Okay, so then we have, so now we have all of our various clues. Okay, so those are all the important clues. And now we want to talk about what the evidence tells us. Okay, so there's a few things that we know. We know that we learned that the acceleration of the car was 3 meters a second squared. We learned that the height of the balconies was 4 point, whoops, wasn't 4. It was 3n plus 2.5 meters. Maybe we should say 3 meters times n plus 2.5 meters. And finally, we learned that the debris field V equals 10 meters a second plus 20 inverse seconds times the diameter of the debris field. So these three things come together. So there are several important things that you can work on. First, we want to figure out, and we also know that last piece, we know delta x equals 12 meters. That's delta x of the car, right? That's the distance the car drove to get in front of the vase and the plant. So we know that the car drove 12 meters. So using this, we can figure out a few different things. First, using delta x equals 1/2 AT squared. Using this value, using this equation, because V naught equals 0 if you start at the stoplight, using this value, we can plug in the distance the car went and the acceleration of the car, and we could figure out how much time the car was driving for. T would be 2 delta x over A. Those are the distance of the car and the acceleration of the car. That would be the square root. And that would be the time the car drove to get in front of the light. And you could calculate a value. And if you go ahead and do this, I will tell you that the value is somewhere between 2 seconds to 3 seconds. So I'll give you that sort of hint. So I'm not telling you the exact value, but it's somewhere between those two values. All right. Once you have that time, then there's a couple other things you could figure out. One other thing we know is that g, the acceleration due to gravity, is 9.8 meters per second squared, or about 10 meters per second squared. It's okay to approximate a bit. So if we know this t, we know that the time the car drove, that is the same as the time the plant fell, right? That's the same time. The exact time that the plant fell is the same as the car driving. We learned that basically from talking to the Uber driver. I think that was clue 5. So since we know that, we could figure out a couple different things. We could use, again, this equation. Instead of calling it delta x, why don't we call it delta y equals 1/2 AT squared. But in this case, it would be 1/2 the acceleration for the plant, right? The acceleration of the plant is just g, the acceleration due to gravity. And t plant squared is the same as this time, right? That time is going to go in there. And we could use that time to figure out the height that it fell from. We could also figure out the speed of it upon impact, right? Because V equals, well, V naught plus AT. The acceleration in this case is GT, but the plant was just dropped, so that's 0 as well. So the velocity of the plant upon impact, right? The velocity of the plant upon impact is just going to be G times, again, that same time we found right here. So that time could go in there too. So we know the speed of the plant upon impact, and we know the height that the plant fell from. Well, now that we know that height, what we could do is figure out what floor it fell from. Remember, we have this model. So once we know this delta y, the height the plant fell from, you could plug that in here and see h equals delta y equals 3 meters times n plus 2.5 meters. And then you solve for this height, for this floor number. Sorry, you know the height. You're solving for the floor number. And if you solve for the floor number, you should be able to determine which floor the perpetrator was on. And you're probably going to get a decimal, but you figure out which one is it closest to. All right. Another thing you could have done, right, is there would be another way to do this, which would be to figure out this speed, right? And then we could say v squared minus v initial squared equals 2g delta y. And we know we dropped it, so that's 0. So we could say that delta y equals v squared over 2g. And do we know this v? Well, we can figure out that v from this equation as well. So v equals 10 meters a second plus 20 inverse seconds times the diameter of the debris field. And that was given to you in one of the other clues. So you could figure out, does the debris field match up to a certain speed, and does that speed go with this height or with that time, right? So there should be two different ways to prove the guilt of the person. Basically, you can demonstrate it by showing the height is the same as a certain floor. You should be able to isolate this floor, right? That would be like saying delta y minus 2.5 meters over 3 meters. That's going to give you n, and that value there, n, that should be close to one of the 3 suspects' floors. And then there is also this v equals 10 meters a second plus 20 inverse seconds times the diameter of the debris field. You can use that and show, does that equal g times t, where t is the time that it took to fall, this time that you calculated, right? And if those two things point to the same suspect, right? If this time, if you get this same time again from that height, the height that it fell from, right? Or that same velocity, then you've shown it two different ways. Okay, so that's what we're really looking for. And you should basically write up your results in this conclusion page, right? So you should show your calculations, and there should be a little writing here. Explain how you know what you know, right? We know the acceleration is 3 meters, right? Explain what these things mean. So it's just a few sentences, sort of explain your logic and how you know who the perpetrator is. Okay, I hope that this helps, and have a great weekend.